So the only thing we have left to learn is Freefall, and this part is great because there's no math involved. Yay, it's just conceptual. So some people are like, yes. Freefall is a state in which the only forces acting on an object are inertia, gravity, and air resistance. Inertia says I want to keep doing what I've been doing or travel at a constant speed in a
straight line.
And that's what would happen, except gravity gets in the way, and then gravity says, no, I want to
go down.
Accelerate you downward. How fast?
-20.
And then air resistance is a type of friction, so it just wants to
Stop.
slow me down. It's a drag, man. That's it. Okay, never mind. When an object falls, of course, the force that is pulling that down is its weight. Weight is the force caused by gravity's acceleration, so gravity is pulling on you, and you have weight because gravity is pulling on you. If gravity wasn't pulling on you, we'd be floating around.
That'd be awesome.
You'd think it'd be awesome, except we would be floating who knows where.
Well, would we have like a boat strapped to us?
Right. That'd be a great. Okay, anyway, luckily we have gravity, we don't have to consider that. So, anyway, weight is our force. So, if I'm chunking you out of an airplane, what's going to happen? You're going to fall. So, as you're falling down, your speed is getting faster and faster and faster and faster. In fact, after 1 second, you're going about 10 meters per second. After 2 seconds, you're going about 20 meters per second. After 3 seconds, you think you'd be going about 30 meters per second. But at that point, you're starting to get so fast that air resistance is starting to become a big factor here. Now, if we ignore air resistance, yeah, you're just going to go 10, 20, 30, 40. Every second, you're going to get 10 meters per second faster, and you're going to get faster and faster and faster. But in reality, if I stick my head out of my car window, is the breeze in my face the same at all speeds? No. At 5 miles an hour, it feels quite lovely. At 65 miles an hour, it's not so fun anymore, right? So as I get faster and faster and faster, the air is pushing on me harder and harder and harder. So what's happening is as I'm falling, my weight is a given speed, but at first, when I'm falling, the air resistance pushing, why is the air resistance pushing up? Because I'm going down. Anytime I want to do anything, friction wants me to do the opposite. It's really annoying like that. So, as I'm falling, my weight doesn't change, unless I'm blowing chunks or something on the way down because I'm scared. But beyond that, my weight is not going to change. But what is going to happen is the air resistance at the beginning is going to be small. But as I get faster and faster, this is going to get bigger and bigger. Eventually, they will be equal. At that point, do I start floating?
No. You just keep falling at constant speed.
Yes. Very good. See, you guys are getting so smart. I can't fool you at all anymore. I used to be able to say outrageous things and you've got yeah! And now you're starting to think. Oh, I hate that. So, yes, at that point, our forces are balanced. When our forces get balanced, then we don't stop moving. We stop accelerating. And then, of course, when we have balanced forces, Newton's first English says we can only travel at a constant speed in a straight line. And so we're going to do that until we either bounce off the ground or until we open up our parachute. Hopefully we open up our parachute because bouncing would hurt. Anyway, the fastest speed at which we can fall, the point at which our weight and our air resistance are balanced, this is known as the terminal velocity. Terminal means end. You get to the train terminal at the end of your journey. So terminal means end. So the terminal velocity is the fastest speed at which I can fall. That is the point where my weight balances my air. Yeah, I'm saying this several times because you'll need to know it on the test tomorrow. So the weight and the air resistance are balanced on my terminal velocity. Yeah. Who has a faster terminal velocity, an elephant or a rabbit?
Do they have the same?
Do they?
Yes.
Do they have the same weight?
No.
So do they have the same balance between weight and air resistance?
Yes.
No. What's going to happen is as I throw you out, how fast does the wind have to be able to go to balance out a rabbit? Less than an elephant. The wind's got to be blowing pretty hard to balance out an elephant's weight. I don't even know if an elephant has a terminal velocity. I'm sure it does, but
it does.
But
I thought weight doesn't affect your speed of falling, only
if
air
you ignore air resistance. But here, I have a nice, beautiful coffee filter.
the air resistance.
oh, that's great.
Did that fall at the same speed this would fall at?
Nope.
Let's do the experiment. No. Okay, so clearly a coffee filter falls much, much more slowly. Why? It's not because it's lighter.
There we go.
It's because its ratio of air resistance versus weight is way different than that one is. And so here, yeah, when do I hit my terminal velocity?
Very fast.
There.
Probably fell about 2 or 3 inches, and it hit its terminal velocity. It sped up, and then, no, I'm just going to go constant. So here, that has a very low terminal velocity. It's not that, oh, it just has a lot of surface area, because if I'm not going to do that to my grapefruit. But if I do this, what's going to happen? Yeah, now it falls suddenly really fast. Why?
Because
The surface area was still the same, but now I had more weight, and so I would have to balance out more. So here I've got like nothing. If I just put a pen in it, then that's a little lighter, but it falls a little bit slower than the pen, but not much. So this would make a good parachute if you're a tiny person. But that's about it. These are fun. You go to HEB and you start opening up packages, and you start tossing these around. And you're like, look, constant speed, and then they come lock you up. Another idiot on aisle 7.
Can we get toy soldiers and like strap it?
Yeah, if you want to. I used to do that when I was little too. But these are fun because they just travel at a nice constant. Yes.
it's also because of the shape, right?
The shape of it keeps it pointed in this direction. Like if I do it this way, that's not stable, so it wants to turn back over to the stable part, but then it keeps saying, no.
Like
Okay.
that one has a hole in the middle, and so
Piece of paper. Do pieces of paper fall fast? Or do pieces of paper fall slow?
Depends on how you hold it.
The weight doesn't change, but the surface area changes, and so the amount of friction changes. If I throw it this way, then the surface area is huge. If I throw it this way, surface area is small. If I throw it this way, it's trying to accelerate really fast, but what happens if it turns halfway through? Now suddenly I need to slow down, and then I go this way, and I need to speed up. And so my terminal velocity keeps changing based on the shape of this. And so if it's just like this, it was going really well for a while, and then whoop, oh, I gotta slow down. And if I try and throw it like this, it was going real good constant, and oh, I'm gonna accelerate. So it changes a lot based on the surface area. So if it was just, oh, it's a small thing, so it should fall at a small speed, then shouldn't it fall at a constant speed the whole time?
No.
I'm saying if it's weight. Many of you have realized or have heard that, yes, a light object and a heavy object will fall at the same speed if we ignore air resistance. So here we're saying, is that really true or not? I'm going to make this smaller so that it's smaller. So here I have a book and I have a piece of paper. I still have it. Okay, I'm going to drop both the book and the piece of paper at the same time. Who's going to hit first? Are you sure? Okay, ready, set, yay! Okay, so we found a use for our ice book here. So the book hit first. Why did the book hit first? Now, some people say, oh, because the book is heavier than the piece of paper, that's why it fell first. Okay, does anybody want to bet me that the piece of paper will fall first? Really? You want to bet me?
I knew you were gonna push it down.
How much?
No, I'm going to drop both of them from this height, and the paper's going to hit first.
Yeah.
How many people will really take that bet?
Fine.
You guys are so gullible. I didn't say I was going to drop my Okay, anyway. Yes, sir. She went home sick. She said she has the flu.
Went home.
Yeah.
Thank you.
Uh-huh. Okay, so in reality, this thing, you think it wants to fall slowly because some people think because it's light. And I'm telling you that this one falls slowly because it's affected very strongly by air resistance. This one not as much. I can prove that if I put it on top of the book. If I put it on top of the book, now it's shielded from the air resistance, right? So if it should fall slowly just because it's light, then when I let go of them, they should pull apart, and this one should fall fast, and this one should flutter down. But if it's just the air resistance and it's being shielded from that, then they should, what do you know, fall together. The other way that we can prove this is if I take this piece of paper, if it should fall slowly just because it's light, then if I crumble it up and I put it into a very small compact container, did it suddenly get heavier?
No.
It's still a light piece of paper, but now is air resistance as big of a factor? No. So now, hey, they hit at the same time. So really, it's not the lightness of a thing, it's how much does air resistance affect it. And light objects tend to be affected more by air resistance than heavy objects do. And so that's how we get this idea that, oh, a light object falls slowly and a heavy object falls faster. In reality, it's just which one gets affected more by air resistance. So if I throw you out of an airplane, is everybody going to fall the same? No, it depends on two things. How heavy we are and how much air. Can you affect how much air resistance you have?
Yeah.
Yeah, if I throw you out of an airplane and you want to win the race to the bottom, how would you go?
Straight down.
Yeah, I mean, if you hold yourself as straight as possible, then you are like the little piece of paper going this way. And if you want to last a couple seconds longer, then you're going to spread yourself out as much as possible, give as much surface area, and you'll go slower. If you've ever seen skydivers and they're trying to hook up to each other, they do that. The guy wants to catch the other guy, and like you're diving, and then he gets closer and he wants to spread out to slow down a little bit more. And so, yes,
Ever gone skydiving?
I have not gone skydiving.
Have been inside the wind.
I haven't. I want to do that, but I'm poor. I'm a school teacher with 6.5 children, so
6.5.
And a half.
it's a long story.
Wait.
My oldest daughter is married, and so I call her husband my half child, just because it's funnier to say 6.5 children than to say 7. I still love Peter, but anyway, getting back to here. Who has a faster terminal velocity, an elephant or a rabbit?
Yeah.
Clearly, the elephant would hit the ground before the rabbit would, because the rabbit doesn't have to fall near as fast before he bounces out. How about if we drop a hammer or a feather? The hammer should win. But what if we took out all the air?
They'll be the same.
They should be the same. Here's an exciting video of a hammer and a feather being dropped. What do you know? The hammer won. Now we're going to go someplace where we have gravity but we don't have air resistance. Where can we go that we have gravity but we don't have air resistance? Yeah, if we're out in the middle of space, then this isn't going to work so well, because then we're going to let go of two things and they're just going to hover there. And it's going to be, that was an exciting experiment. But we have an atmosphere here on Earth because we have a nice strong gravity. And so gravity is pulling in on the air and it gives us a nice substantial atmosphere. But if you go to some place that is smaller in mass, it's going to have less gravity. And so what happens is it's not going to have enough gravity to hold in air. And that's the case on the moon. Here on Earth, we are at 9.8 meters per second. On the moon, you're about 1.6. So I would have substantial hops on the moon. but I don't breathe there because it doesn't have much of an atmosphere. It's pretty insignificant. So here we have an exciting video of on the moon. So I'm going to show you this little clip, and you're going to listen to Neil Armstrong talk, but you need to listen, and you need to know one piece of information. Everybody that's my age knows, because it was real common knowledge at that point, that the little landing module was nicknamed the Falcon. If you understand that, what he says will make more sense.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
You'd think for $1 billion we would have gotten better video quality, but that's the best video quality that was available back in the late 60s. So that was pretty cool. So when he dropped them, notice how they almost looked like they were falling in slow motion?
Yeah.
Because gravity there is, if they were both falling in slow motion, then the hammer still would have beat the feather just in slow motion. He would have been on Earth.
Unless it was fake.
Well, how come the video quality was that bad? There was TV shows back in the 60s, right? So they
Have you
broadcast-
seen the TV shows back in the 60s?
They were
It was in the moon. You're watching that
They
on
look
new
pretty-
TV.
The video quality wasn't that bad. Wasn't that good. Plus, you're sending this a little bit farther too. So you have to boost up the signal a bit, and that introduces noise. But yeah, you weren't alive in the 60s. You don't know what the video quality was like on TVs back then.
Oh, there's YouTube.
I was.
But there's YouTube. Thanks to the lighting, it only has one leg, so.
Yeah.
the lighting.
Isn't it beautiful?
Yeah, they should turn down the sun.
Okay. Yes.
Come on, son.
Anyway, I would like to, before we get, we already did this one another time, but I would like to talk about people jumping out of an airplane.
That's fun.
So, okay, I am in an airplane with you. We get up to a nice cruising altitude, and I shove you out the door.
Okay.
What's going to happen to you?
Die.
No, you're not going to die. I didn't say you weren't wearing your parachute. We're up in the airplane. Okay, anyway, I always prepare you. So, I throw you out of your airplane, you are wearing your parachute, but initially you get faster and faster and faster and faster because the Earth is accelerating you down, right? But you're going to accelerate only until you reach your, which is the balance between your air resistance and your weight. So you've hit your terminal velocity, you are falling as fast as you can fall, so for you that's like 120 miles an hour. So somewhere around in that area. What? That's not bad at all. So you're falling at a nice 120 miles an hour, and then you decide, I've had enough of this, man, and you pull your parachute. What happens to you?
You just look at your spikes.
You get a negative acceleration.
Okay, here's the deal. If I would have asked this question back in the 60s, everybody would say, when you open up your parachute, suddenly now we have what kind of air resistance?
Large.
Bigger air resistance. If we have bigger air resistance, then we have a net force going upward, which means if I'm going this way at 120 miles an hour and I get a net upward force, that's going to be a positive or a negative acceleration on me. It's against my motion. So, yeah, so that's going to slow me down. And people would just say, oh, the parachute opens up, and you would slow down to a new terminal velocity, hopefully one that you can land and walk away from and not bounce and die. So that's the whole point of a parachute, is you have so much surface area now that I have a much slower terminal velocity, one that I can land without breaking anything. But you guys have been raised in a completely different age. And most of you guys think, as soon as I open up my parachute, I go up in the air, and then come slowly back down. If that happened, first of all, you would be dead. Because if I'm already going 120 miles an hour this way, and then suddenly I go that way, that would mean that in that brief instant I would have to reverse directions, and you know what I'm saying? This would be really, really painful if you went from 120 this way to say even 5 this way. That's gonna hurt. But you don't. And you're saying, but Paul said, I've seen it.
You keep going down the chest.
This is the problem. You've seen it.
Right.
You believe that it's true because you've seen it. You trust your eyes. I've seen this happen a million times. What happened was in the mid-70s, a movie came out where James Bond got thrown out of an airplane. He did not have a parachute. He had to chase down another guy, wrestle him in midair, steal his parachute from him. Then he opened up his parachute, and everybody on Earth saw James Bond go zooming up in the air as soon as his parachute opened. And from that point on, it showed up in a million different movies and a million different videos and X Games stunts and everything else imaginable. And we are all convinced now that as soon as I open up a parachute, I go up in the air. What you fail to consider is camera angle. Who's filming this thing? Somebody else who is falling. You're not filming this from the airplane, because if so, you would look like a little dot that disappeared very, very quickly. And so that can't work. The only way this can be filmed is if somebody is falling right next to you with a camera filming this whole thing. Now, if you're falling at 120 miles an hour and he's falling at 120 miles an hour and you open your chute, you slow down. So relatively speaking, you are higher up from the camera angle, so it looks like you're going up. It's like you're on the interstate. How many people have been on the interstate before, and you're going like 70 and the car next to you is going 65? If you just look at his car, he looks like he's going backwards, right? Is he really going backwards? No. He's still going forward really, really fast. He's just going slower than you are, so it looks like he's going backwards. Same thing's happening as I fall. If the parachute slows me down, I'm going to be falling less fast as the cameraman, so the cameraman's down looking up at me, and so everybody thinks I open up my parachute and I go up in the air, which that would rip. I mean, it's seriously, if you went up in the air, if you're falling 120 miles an hour that way and just came to a complete stop, what would your body want to do? Keep going at 120 miles an hour, and these little straps connected to your legs would go, and you would have no legs anymore. Yeah. Understand what I'm saying? I like to do this because, like I said, you guys, I saw it in the movie, so it must be true. I opened it up, I go up. No, you would die. So that would be bad. Okay, does anyone have a question? Zoe? How much wood would woodchuck chuck if woodchuck could chuck wood? Okay, does anyone have a question that won't make my headache worse? You mean teachers don't know everything? Yeah. They don't. Okay, Odie, let's see if you're worthy of being the Cape Avenger's high-performance mode of transportation. Faster! Faster! Stop! Seatbelt. The Cape Avenger needs a seatbelt. Which E-wish is this demonstrating?
The second one.
First one. When Odie stops, Garfield wants to keep doing what he's been doing until he hits that unbalanced force of friction there. One of the things on the test that you're going to have to do is you are going to have to identify some E-wishes. You'll also need to know your vocabulary. So again, if you look at your Unit 3 problem sheet, up at the top, there are a bunch of vocabulary words. And pretty much like last time, those of you who studied did really, really well. Those of you who just said, I'm going to wing it, not so much. So check on that. It will be matching. It will be easy. I will have a multiple guess section.
Yeah, multiple guess.
And the multiple guess section will have several things in it. In problems A, please circle number 7 and 8. Number 7, we said, what are Newton's 3 E-wishes, giving examples of each. So I will give you some examples of something that's happening. So if I say, Odie stops and Garfield keeps going there, you'd say, oh, that's totally Newton's first E-wish. If I say, I kick a soccer ball and I kick Bob, and the soccer ball goes really well, and Bob just breaks my foot and barely moves, that would be Newton's second. The big mass has the small acceleration, the smaller mass has the big acceleration. And Newton's third, which says, if I punch someone in the face and my hand gets broken, that's because
You hit your hand as hard as he hit
his face hit my hand just as hard as my hand hit his face. That would be Newton's third huge. So we've got that kind of thing going. So number 8 asks for the forces, and again, the very last time we took a test, I gave you this piece of paper and it had all the forces, so you'll need to know those and stuff. So again, they'll be in matching and they'll be in multiple guess in that section. If you circle number 4 and number 9, those will be math problems. And you're saying number 9 doesn't look like a math problem, man. Well, if I drop a rock, the Earth's gravity accelerates it downward according to Newton's third. The Earth accelerates.
Yeah.
What's the opposite?
It goes.
So if I have a rock, it's getting pulled that way, and the rock is pulling the Earth that way. The force between those two would be equal. Is the acceleration equal? No, because this little tiny rock has a little mass, and it has the acceleration due to gravity. And then that big mass of the Earth is going to have a acceleration. So if you're doing this formula and you solve for this A and you get a big number, you're doing something wrong. But that should be an easy problem, right? In fact, this is the easiest problem that'll be on the test. It's the only problem on the test where you only have to use one formula. So it's where I'm dropping something and I want to see how fast the Earth comes up. That should be the easiest one on the test.
What's the wind?
What's the rule?
Wind resistance.
So wind on the Earth.
We ignore the air resistance.
Oh,
But yeah. So that one will be total simple. Everybody will dominate on that, and there'll be some of you that just says, I didn't get that problem, it was so hard.
Could you give an example?
Yeah. In problem C, I want you to circle number 4, 5, and 13. So if you know how to do 4, 5, and 13, you got it made, baby. And of course, 4 was real easy after I taught you the cheat notes yesterday. And 5 is just throwing your mom up in the air, so that one's fun. And 13 was the tricky one, but we can do that later. And in problem D, I want you to know everything. And you're like, everything? Well, yeah, it was just some vocabulary about freefall and stuff, so what we were talking about today. So that should be really easy to do. So this should be easy. If you know all that, you should totally dominate, and that's what I want you to do. I have a whole lot of Smarties to give out, and I'm ready to make you smartier.
Can you do an example of the